Hi, this is Mr. Champlin, and we are looking at Chapter 2 that's concerning kinematics and specifically motion graphs. Let's begin. Motion graphs are a way to describe motion using a graph, and there are three types of graphs: position versus time, velocity versus time, acceleration versus time. And they're showing a continuous display of what is going on with the object as it moves in regards to those three variables: position, velocity, acceleration. So here's the situation. A car is located to the left of the origin and is slowing down to rest as it moves to the right. So I'm going to go ahead and draw an axis. It's going to the right, but it's located to the left of the origin. So here's my origin. It's starting here. I'm going to go ahead and draw a motion diagram. So my motion diagram, the arrows are going to get progressively smaller because it's slowing down. And then eventually it stops, so that would be a dot. So there's our motion diagram. Arrows are getting shorter as it slows down. So now to draw the position time graph, I'm going to go ahead and see if I'm going to get this drawn here. So I'm going to start my axes here. Position time will be on the top. Typically that's what happens. Then velocity time. Then acceleration time. X, V, and A, and all of these axes are always T. Okay, so it's starting, here's the origin, so this would be the origin for position time. We're starting behind it to the left, or in the negative range, so we start here. Now that we're going fast, the arrow is long, so that means it's going fast, so therefore it's steep. As time goes on, it gets less steep. So it's going to look like steep, and then the curve and flattens out by the end. For the velocity time, we are initially moving fast forward as the arrows show, but then we're slowing down to rest. So I'll start up high along my velocity time graph, and then as time goes on, I'm going to slow down. Okay, so that's slowing down. Acceleration, it is always slowing down throughout, so that would be a horizontal line below the axis since it's slowing down. So I'll just draw a horizontal line below the axis. Alright, let's go to the next slide. Position versus time graph. Horizontal line represents a stationary position, so whenever a horizontal line, you're not moving. An angled line upward indicates motion away from the reference position. Okay, upward, angled away from reference position. An angled line downward indicates motion towards the origin. A curved line represents acceleration. Concave curve upward represents positive acceleration, and concave downward represents negative acceleration. And to the right, I'm going to show you adjacent graphs represent three motion graphs for a car slowing gradually to a stop and then accelerating quickly. So let's analyze these graphs. Alright, I know there's a lot going on here, but let's see if we can figure it out. And right here we have the position time graph. We are starting at the origin. You can see the line is going upward away from the origin, but it's curving concave downward. Concave downward means slowing down. So it's going fast quickly, or initially it's going fast, but it slows down. And then when it's horizontal right here, that means there is no motion. And then as it's like a stoplight, it's going to accelerate back, so it picks up speed, and the slope gets greater and greater as you go along here. Now, these should show that same motion, going forward fast, way above the origin, and it slows down to 0 where there is no slope right here, and then it speeds up going forward, and so therefore it's going diagonally up. And it looks like, based on the steepness of this line compared to this line, it looks like its acceleration is greater here than here. The acceleration graph is now basically the graph of the slope of this graph. Well, the slope of this graph is negative. It's a negative acceleration. So notice it goes, here's the origin, 0. It's below, straight line below. And then at this instant, it starts accelerating forward. So then the slope of this line is positive. So therefore I draw a horizontal line representing the acceleration at that point. We know that velocity times time is distance, rate times time is distance. The change of the position of an object is equivalent to the velocity multiplied by the time interval. On the velocity versus time graph, the area below or above the graph is equal to the displacement of delta x. The area for squares and triangles are simple to calculate. You've learned that in grade school. The area of a square is base times height, and triangle half base times height. So those will be the ways that we're going to determine the area. We could integrate when we learn how to do that later on. Example, determine the object's delta x over 10-second time interval and create a position versus time graph. So here is the graph. It starts off at moving negative 5 meters per second. So that means it's moving to the left. But as time moves on, it slows down to 0, and then it speeds back up to 5 meters per second forward. And then for the next 6 seconds, between 4 and 10 seconds, it maintains a constant speed. Basically, I just said that. Okay, so now to determine the displacement, you take the area. Well, if you look at this triangle, in this triangle, they are similar triangles. One's positive area, it's above the axes. This is negative area. So to get the net displacement for the first 4 seconds, it's going to be 0. And then the remaining 6 seconds between 4 and 10 is 4 to 10 is 6 this way horizontally and 5 this way. So you figure that out. That is 30 meters per second. So here's our graph. We're going backwards, negative. So here's our negative slope. We get to this position. We have no velocity, so that would be at the very bottom of this curve. The slope is 0. And then we get back to the 5 meters per second going forward. So theoretically, this slope here should be equal to that slope there. And then from that point on, it's moving at constant speed, so therefore the slope of this is constant, since the slope of a position time graph equals is graphed in the velocity versus time graph. And this slope never changes. Therefore the velocity shows no change. Acceleration versus time graph. The acceleration is equal to the rate of change of velocity per unit of time. For example, if the acceleration is 5 meters per second squared and the object begins from rest, then the object will increase its velocity by 5 meters per second in each second. By the third second, if you're increasing 5 meters per second, you'd be going 15 meters per second. After the next second, you'd be going 20 meters per second. So it just continues that pattern. Acceleration versus time graph can be used to create a velocity versus time graph. So the area underneath a acceleration versus time graph equals the velocity time graph. The area under velocity time graph equals the position time graph. The only thing, note the initial velocity or position cannot be determined from the graph, like from a velocity time graph. You cannot determine the position because they're not graphing position, they're only graphing velocity. So the problem would have to give you an initial velocity or initial position. Create a velocity versus time and position versus time, and a motion diagram for the acceleration versus time graph for motion of the moving object described below. The initial velocity is 10 meters per second and the position is negative 10 meters. It maintains its initial velocity for 3 seconds, and then then it slows at a constant rate to rest in 3 seconds and remains there for 3 seconds. So I went ahead and did this one for you. So let's see. Given this velocity time, it maintains 10 meters per second. Say the initial velocity is 10 meters per second. It maintains it for 3 seconds. So this is supposed to be 3 seconds. Then it slows it to a rest in 3 seconds. So it's slowing to rest in 3 seconds. Same time interval. So this would be 3, this would be 6. And then it remains at rest for 3 seconds. So I like to look at, based on the information they gave us, I would like to start with this graph. So let's go down to the position versus time graph. It says its initial position is -10. So you're below the origin at -10, and you're maintaining a constant speed. Constant horizontal line. So it would be a diagonal line here, constant speed, slope doesn't change. From this point on, it starts slowing down. So the curve decreases to its 0 at this position. And then there's no change in position, so it's flat. Velocity is 0, so it should be flat. If you jump up here to the acceleration versus time, you have no change in velocity, no slope. So therefore the acceleration is 0. You have a negative slope here, so therefore the acceleration line is straight across. And then again, no slope here, so it should be horizontal again. So let's do one problem here, an example problem. A lead ball is dropped into a lake from a cliff, and the ball falls for 2 seconds before hitting the water. After hitting the water, it sinks to the bottom with a constant velocity equal to the velocity with which it hit the water. The ball reaches the bottom 3 seconds after it is released. So I guess the total time would be 5 seconds. Assume gravity is 10 meters per second squared. Okay. So we're going to draw a position versus time graph. And I'm going to go ahead and draw it. We call these stacking the graphs. It's just a little easier to keep track of everything. So this would be position, or x. This would be velocity. Both of these are time. Alright, it says it is falls for 2 seconds. Well, it's going to fall from rest. And we're going to have the axes pointing downward. So we're assuming 0 is at the top. Okay, so I guess if I was to draw a motion diagram, it would look like this. This is 0, and then it picks up speed, and then it maintains, once it hits the water, maintains constant speed. Arrows would be the same length after it hits the water. So it starts at 0, and then it picks up speed. Then it maintains a constant speed. Diagonal line. Let me get rid of that. Okay, so this would be at the point of hitting the water, and then it falls another 3 seconds. So let me write that down. So this is 2, and this would be 2 plus 3 is 5. All right, so picking up speed. So velocity is picking up speed. Then maintaining a constant speed. This is 2. This is 5. All right, how fast can we determine how fast? Well, I told you the acceleration, gravity, is 10 meters per second squared. So that means per each second it increases 10 meters per second. So after 2 seconds, it's going to be going 20 meters. And then it's going to maintain that. So now we have to figure out how deep is the lake. Okay, well, we look at the area. Remember, the area of velocity versus time graph equals the displacement, or how far it's traveled. So we have a triangle here. Look at, I'll just shade this in. So the area of that triangle, it's 1/2 base, or 1/2 2 is 1. 1 times 20, so the area here is 20. So this is 60 meters. So the total distance it fell was 20 plus 60. Total distance, delta x, is 80 meters. So the length in the lake, or the water depth, would be 60. That's what's left over when it's maintained.